I would like to thank the opportunity to speak here. I mean, this is really important to me, especially because I have a different background from most of you. I spent most of my life actually working with quantum information and quantum foundations, but I'm moving towards quantum many-body physics for the past couple of years. So it's really important to me to get to know people from the field, and especially, as Klaus put it yesterday, the shooting stars of the field. So I'm learning a lot in this conference. I'm really enjoying all the talks and learning a lot of new stuff here. So as Diego did yesterday, I will first put my talk in perspective by changing the title of the conference a little bit. So basically, the subject I'm going to talk about is like that. I will focus on local quenches mainly, and also my main object is entanglement in a many-body system. And actually, I will look regimes where there is not a strong entanglement between parts of the system. So before I'm going further, let me tell you a little bit about my origins. My city is called Belo Horizonte. So here it is on the map, so you have a rough idea of where it is. So Rio de Janeiro and São Paulo are somewhat close to it. Here's a picture of it. I mean, we don't have the Alps or the Andes next to it, but we have this nice mountain. It's a nice place. And also, I put this picture here to show you that some myths about Brazil are actually true. I mean, it's quite common to see these monkeys roaming around my university, the campus of my university. And actually, next to my house, I sometimes see these small monkeys just walking around. So, even though it's I don't know, it's a 3 million people sized city. So let me return to the subject. So in the original title of my talk, I use this expression, which may be puzzling. I mean, I'm really using the word spreading in the spatial sense. I'm talking about something spreading in space. And entanglement is this non-local property you can define in quantum physics. So how something that is non-local can spread in space. It may be confusing in principle. So let me spend a few minutes explaining exactly what I mean by that, about entanglement spreading. So let's picture some quantum chain. It doesn't matter exactly the details, so we just have a bunch of spins. They can interact with each other. And imagine that you can do some perturbation, or basically a local quench in a small portion of this chain. And imagine that you look at this quantity here. So you're gonna follow the magnetization, let's say in the Z direction, of spin in position X of the chain, for two situations. One where you do not do this quench, and for a situation where you do that quench. Okay, so I guess the most easiest case to consider is the one where you have the chain in the ground state, for instance, or any steady state. So this thing here actually does not depend on t, so just on the position of the spin. This will just give you the profile of magnetization of your chain, of your steady state. But since you have done some perturbation, like in the Hamiltonian or in the initial state, this thing here can evolve in time. So you're probing the change of magnetization in each spin of your chain due to their to that local quench. Okay, so you have, that's what I'm calling changing magnetization, and this is something that will depend on the position of your spin and on time. Okay. So if you look at this kind of quantity, here I'm showing a T-DMRG simulation of a quantum chain. I will not enter in the details of this model and these computations, but here in this color map, on this horizontal axis, I have the position of the spins in a chain. Here we have time, and the color diagrams tell us the magnetization of each spin for spin in position x and instant of time t. Okay. So you see that we have this kind of profile. Note that the white means 0. And so below this line here, you basically do not have any change in magnetization. And of course, this is due to the fact that since you have done a local perturbation, this will propagate in the system with a finite velocity. Okay, so here we have some snapshots of the magnetization profile for several instance of time, and we see that it propagates like a sound wave, right? Like we saw yesterday in cold atoms, right? So, on the other hand, we can look at this quantity. Instead of looking at magnetization in several points of the chain, I can cut my chain into halves in several positions of it. So x here now means the position where I made a cut into, where I split the chain to compute the entanglement between each side. Okay? And again, I can look at how this entanglement changes with time due to some local perturbation. So this quantity will again depend on the position where I have done the cut and the instant of time. And if you simulate this, you again see this kind of profile. Note that people in this field usually call this a light cone, because this kind of profile resembles the light cones we have in special relativity. Right, the casual cone defined by an event. And so at the end of the day, we see that this change in entanglement also spreads in space pretty much like magnetization or any other quantity. Okay. Of course, what happens exactly in that region, it's pretty dependent on the particular model you are dealing with, but the fact that it spreads, it's general, and the main objective of this work is to prove that, okay, for a large class of models, to prove that indeed entanglement should be very small, this change in entanglement should be very small in that region of this diagram, okay? So, actually, since I'm going to use non-relativistic quantum mechanics all the time, this will be not exactly 0, but will be very small. That's the best we can do with a non-relativistic theory. So I will focus specifically on the situation where the chain is, or actually the initial state of the system. I will not be restricted to chains, but I will focus on the situation where the initial state is pure, and the evolution will always give me a pure state, and I will focus specifically on the entanglement entropy of a given bipartition of the system. So basically, I will denote by X a region where you can do some quantum quench, and what I will have to do is to probe and to estimate the change in the phenomenon entropy of the reduced state of the chain in some region Y. So what I'm going to talk to you was published here, and it was done in collaboration with Natalia. I guess nobody knows, everybody knows her. And the main tool we have to use to prove what I'm intending to prove is a Lieb-Robinson bound. This was something that was first proved in the 70s, but in the past 10 years or so, we saw a surge in the use of this kind of inequalities. They are being used to prove several interesting results in the field. So let me explain a little bit what is this kind of bound. And then we can picture a quite general spin system. I mean, the lattice can be whatever you want. It doesn't need to be a chain. It doesn't be anything in particular. It's important, though, that the interactions are short-ranged in some sense. But as long as you have this kind of model, I will discuss a little bit more about the conditions you need to have a Lieb-Robinson bound. But basically, we can picture any spin system with not so long-ranged interactions. And let's imagine that you distinguish two regions of the system. I mean, two subsets of spins in your system. I'm naming them X and Y here. It can be anything, any portion of your system. Let's say that you take local observables on those regions. Let's say we have observable A and B. And then a Lieb-Robinson bound is an inequality of this kind here. So on the left, in this term here, we have the evolution of observable of region X in the Heisenberg picture. On the right-hand side, we have a bunch of constants here, but D is actually the distance, the spatial distance between sets X and Y. T is time, mu and V are constants. And the idea that I'm writing this constant as V, because we can read it as a velocity, indeed. Because as long as this term in parentheses here is positive, right, or if it's large enough, you have something very negative in this exponential, and this thing will be very small. Yes? The norm of A? No, because we are in the Heisenberg picture, and this kind of evolution does not change the norm. So it doesn't matter at which instant of time we compute the norm. So we can read this expression in a diagram. Basically, the inequality is telling us that. Okay, if you look at this diagram, where here you have the distance between the two sets, here you have time, then below this line of inclination 1 over V, this quantity is very small. Okay, it's not 0, but it's very small due to this exponential factor here. So the problem with this inequality, at least to me, I'm from this information community, and first of all, we almost never use the Heisenberg picture. It's difficult to talk about entanglement in the Heisenberg picture. It's difficult to talk about an open system in the Heisenberg picture. It's more difficult to do things somehow in this field, in this picture. So we don't have much intuition about it. More than that, we have a commutator between two operators here, and it's difficult to have an intuition. At least I have difficulty to understand such a thing. And also we have the Neumann of an operator, which is something that, again, it's difficult to understand. So it's difficult to me, at least, to understand what is going on the left-hand side of this inequality. But we can use it to prove several things that I believe, at least to me, are easier to follow and to picture. So let's consider this situation where we can do some quench in the system. It can be either in the initial state of the system or in the Hamiltonian. You can change some parameters of the Hamiltonian in this region X. And then you can try to probe the effect of this local quench on a distant region Y. You can try to measure some observable in that region, and you can try to see if you see any change due to that perturbation. So again, here I have the expected value of some observable in that region, and it evolves in time due to some unperturbed evolution, but it can also evolve in time after this local quench was done. You can see some change, and if you do use the Lieb-Robinson bound, you can prove an inequality of this kind, and this shows that this observable will not be significantly perturbed in that region of this space-time diagram, okay? Which again makes a lot of sense, right? Because if you do some perturbation, you have to wait a little bit for that information to propagate in your system, and you see some changes in a distant portion of it. And from this inequality is actually easy to prove another one for the reduced state of that region, okay? If this inequality holds for an arbitrary operator or observable in that region, you can readily prove that inequality for the reduced state in that region. So it shows that the reduced state of the region as a whole is not very perturbed in this region of the space-time diagram. Okay. Okay, so now remember that my objective here is basically to obtain this kind of inequality, but for the von Neumann entropy of the reduced states in that region. That's my objective, okay? So we know that this entropy is a continuous function of your state. So given that the state and its perturbed version are very close to each other, it seems reasonable that their von Neumann entropies will also be very close to each other. So it seems quite plausible that we can derive this kind of inequality for the entropies of the states, the von Neumann entropies. And this is indeed possible. This was done. So this is getting close to what I am intending to prove. So you have this kind of Lieb-Robinson bound for the von Neumann entropy of reduced states of your system. But basically, the bounds we had before had this term here. So it was proportional to the volume, I mean, just basically the number of spins in region Y. So that restricts a lot the range of applicability of the bound. If you have a very long chain, or if you have anyway, if your whole system is too large, the bound will be useless, okay? I mean, I would like to apply such kind of bounds in regions Y that can be extremely large, at least in principle. So what we did was exactly that. We managed to prove a bound without this volume dependence on the region Y. So we can apply, for instance, to show that the very beginning of my talk, where I showed this behavior for the change in the entanglement entropy of a chain, we can apply it to show that this kind of behavior will take place even if the chain is infinite or however large you want. Okay, so that's my main message, and I will just give a very vague and brief proof about for this inequality. I will not enter in any details, but if someone is interested, we can discuss later. I mean, I'm hiding a lot of details here, so it's not true that on the right-hand side here we don't have any dependence on these sets x and y. I mean, these constants here, it's not exactly a constant. It depends a lot of things, the parameters of your model and things like that. It has some dependence on the sets x and y, but I mean, the essential thing is that it does not depend on the volume, on the number of particles of region y. This is the important feature of our bound. So basically, what we explored is that since we are estimating the change in the von Neumann entropy of the reduced state of an extended region y, we basically explored the fact that if you have done some quench in region x here, never mind these two regions here. Imagine that the quench was done here. So we have to wait a little bit until the effect of this quench propagates and changes your reduced state in region y. Okay? But we do know that if you look at portions of your region y that are more distant from your quench, we also know that these regions will have smaller changes in the reduced states. Okay, so we basically explored this fine geometrical information about the system, and in our proof we use basically two ingredients. Our starting point was a Lieb-Robinson bound. We assumed a model that satisfies this. And so it's worth mentioning that this is very general. I mean, it holds for basically any model that has short-range interactions. I will not get in the detail how short they must be. I mean, you can go beyond finite range interactions. You can have, let's say, exponential decay with the distance and things like that. But it's also important that you can allow for each system to have a Hilbert space with infinite dimension, but you cannot allow for interactions described by operators that have infinite support. I mean, in the algebraic sense, the linear algebraic sense. So it's possible to give examples where if you violate this condition, you do not, your system, your model do not satisfy a Lieb-Robinson bound, and also if you violate it, or this is more easy to understand, right? If you allow for a very long-range interaction, then you don't have to expect to satisfy that kind of bound. But also, this condition is quite intriguing, that if you do violate it, things can propagate in your system very fast. And so these bounds hold in a very general settings and models, but to have our bound, we have to use a little bit more of conditions. Basically, but they are still quite general. I mean, we just have to assume that the system, your lattice, has finite fractal dimension. This basically says that if you take balls of sites in your system, the number of sites inside this ball will grow algebraically with the radius of this ball. So this is one way of satisfying this condition. So it's quite natural. Okay, any real physical lattice satisfies this. Yes. What? Yes, for sure. Yeah. So I mean, most of the lattice satisfies this. You have to consider really exotic lattice to violate this condition. Well, so I will show you the proof in just this slide. So this is not a proof, okay? It's just the core idea of the proof, where we explore the fact that if you, so I'm distinguishing here a region of the system, okay, a bunch of spins of the system, and we are trying to estimate how the von Neumann entropy of the reduced state of the region changes due to your local perturbation. And to explore this idea that this perturbation, that this change will be smaller as you move away from the region where the quench took place, we basically wrote this changing in entropy in that way as this telescopic series here. I mean, we are just summing and subtracting zeros. But every time we gather a pair of terms like that, we can write this in terms of the so-called conditional entropy. And for this conditional entropy, we have a very strong bound, which is for changes in this entropy, which depends only on the Hilbert space dimension of the smaller portion of your splitting. So the thing is that this factor appears here in this bound due to the fact that some inequality is used where you relate variations in entropy with variations in the reduced states of your system. And this bound is dependent on the Hilbert space dimension where your density operator lives. So in this case, in a many-body system, the Hilbert space dimension of any portion will be proportional to the volume, to the number of sites of that region. So that's what's the problem here with this bound. That's why you have this volume dependence in the bound. But by exploring this finer inequality for the conditional entropy and the fact that the effect of the perturbation is less and less, sorry. Yes, it's finite. Well, as long as this region Y is finite, but I'm always in a finite setting. Okay, I always assume that my system is finite. I'm not working in the thermodynamic regime in any instance. And well, I guess this. Okay, this is just a very rough idea. Okay, the proof is quite detailed with several constants, and I don't think there is a point in showing every detail here. And well, essentially that's my message. We managed to prove that the von Neumann entropy of a region satisfies the so-called light cone effect. Okay, it does not vary too much due to your perturbation, as long as you are in this region of the space-time diagram. And well, that's basically it.